Okay, let me write the title of the talk, and then please ask a lot of questions. I'm not sure I'll be able to answer them, but please ask. So it's about, the title is a PSPACE construction. Of a small heating set for the closure of small arithmetic circuits. Arithmetic or algebraic circuits. And it's a joint work with Michael Froese. It doesn't go up. Okay, so I think I'll spend the beginning of the talk just explaining the title. So I want to explain what are arithmetic circuits, what are heating sets, and then what's the question of the construction problem. Okay, so an arithmetic circuit okay, so for those of you who know Boolean circuits, they are similar to Boolean circuits, just using the operations of plus and times. But for those of you who don't know, so basically we have a set of variables, x1 up to xn. And we want to compute polynomials on those variables, and the way we do it is we have the variables at the bottom, and then we take some operations of them. We can take plus, and we can use the intermediate computations to compute more polynomials. And we are also allowed to use coefficients from some underlying field. There is some field in the background. In this talk, the field will be either the reals or the complex numbers, but arithmetic circuits make sense over any field. And so, for example, you can take linear combinations. Like you can take two coefficients and you can write them on the edges or whatever. And then this gate will compute the linear functions alpha 1 times x1 plus alpha. Then this will compute the product of this result with, say, x3. And you can use the same variable many times. And this way, you do some computation, and the polynomials propagate. And at the end, there is some resulting polynomial. Okay, so these are arithmetic circuits, and they are considered the most natural model for computing polynomials. Okay, so is the model clear? Good. Right, so we will be interested in studying, okay, so what's the interesting complexity measures associated with arithmetic circuits? So there is the size of the circuit, which is basically the number of gates in the circuit, or the number of wires. And there's the degree of the circuit. So by repeated squaring, you can get very high degree and very low size, but we will be interested in circuits that have whose degree is like polynomial in the number of variables. Okay, we will restrict our attention to circuits that compute polynomials of polynomial degree. Okay, so usually we'll denote the degree by r, the size by s, and the n is going to be the number of variables. Okay, so these will be our three measures that we'll be interested in. Okay, so these are arithmetic circuits, and what are the interesting questions related to arithmetic circuits? So, so one basic question is proving. Okay, so what do we consider as efficient computation? So there's a class of VP, which is the analog of the Boolean class P, perhaps, or non-uniform class P, which basically, since we are interested in asymptotic results, so we speak about families of polynomials. So VP is the class of all families of polynomials that can be computed efficiently, where efficiently means that the size of the circuit is polynomial in the number of variables. So for example, so it's like the families or it's the class of families of polynomials that have poly-size, poly-degree circuits. So for example, if we look at the let's say, n by n determinant, so think about X as having n square variables, so it's like a symbolic matrix, and we want to compute the determinant polynomial. So that's a polynomial in n square variables of degree n. And it's well known that this family is, so each determinant can be computed by a polynomial in n arithmetic circuit. Okay, so this family is in VP. Another polynomial family that can be seen in VP is, for example, if we take matrix multiplication. For example, I don't know, if we want to multiply like an n by m matrix with an m by k matrix, and maybe take, I don't know, take one output of this and whatever, or the trace of that, that is also, there's an efficient arithmetic circuit for it. So that's a class of VP, and it captures what we call efficient computations by arithmetic circuits. So one basic problem is to show lower bounds for arithmetic circuits, to show that some families of polynomials do not have small arithmetic circuits. And the most important question here is like, so that's the VP versus VNP question. So I'm not going to define VNP, but VNP can be seen as some analog of NP in some sense. But another way of stating this question is asking if we look at the permanent polynomial. So let me just write the definition in case you haven't seen it. So the permanent of a matrix X is similar to the determinant, except there is no sign, just a summation of all permutations. Right? So the P versus NP, VP versus VNP question basically asks to prove that this family is not in VP. Or in other words, to prove a lower bound on the circuit size of computing the permanent. So that's one of the basic questions related to VP. Okay. So this is one of the most important problems in complexity in general. But in this talk, we'll be interested in another basic problem related to arithmetic circuits, which is a question about the randomization. So the basic, a basic problem concerning arithmetic circuits is called the polynomial identity testing problem. And that's the problem that asks the following. So given some arithmetic circuit with plus, time, etc., over n variables, we have to decide whether the circuit computes the identically zero polynomial. Okay? Or equivalently, given two arithmetic circuits, we have to decide whether they compute the same polynomial. Because by just subtracting one circuit from the other, we reduce to this problem. So turns out that this problem, so this, of course, to compute it deterministically, it seems difficult because we have to, if we just want to write down the polynomial, we have to just follow the computation, and it may have exponentially many monomials on the way. Maybe everything cancels out, but on the way we can get exponentially many monomials. So doing it deterministically in the brute force manner seems to take too much time. So the basic question is, can we decide the polynomial identity testing question in polynomial time? Okay? And it turns out there's a very efficient randomized algorithm for the problem that we all know and like. It's follows from the Schwarz-Siepel-DeMillo Lipton lemma. So the Schwarz-Siepel-DeMillo Lipton lemma basically says that if we have a non-zero polynomial, if f of x is non-zero of degree r, then f of some input alpha, let's call it v, I don't know, not zero when with high probability if we pick v from a set of size, I don't know, 1, 2, some polynomially size in the. So basically, the lemma says that if we evaluate a non-zero polynomial of degree r on a random input, where the random input is just chosen from a large enough set polynomially related to the degree, then with high probability it will evaluate to a non-zero value. Okay, so this is a very efficient algorithm to decide the PAT question, but it's a randomized algorithm. And the basic question, therefore, can we solve the polynomial identity testing deterministically in polynomial time? So this is one of the most basic questions related to arithmetic circuits, and if the question about the permanent is the analog of VP versus VNP, then this can be seen as some analog of deciding whether BPP is in P. So this speaks about RP, but anyways, this is some basic randomization question. And if you look at it, then maybe many of the randomized algorithms that we have can be actually reduced to the PAT question. So, for example, there's a famous algorithm by Kaltofen and Traeger for that given an arithmetic circuit, you want to compute arithmetic circuits for each of the factors, because maybe the polynomial that you compute is reducible. And it is known in there are efficient randomized algorithms for computing the irreducible factors of small arithmetic circuits. And it turns out, I mean, that's a joint work with Shubangi and Swasik, that you can do factoring deterministically if and only if you can solve the polynomial identity testing deterministically. So it captures many of the of the question about the randomizations that we have in the algebraic world, and it seems like the most general one.
Is there a formal way to say that?
Yeah, it's just study.
No, I mean, about the factorization, yeah, that's a result. But
no, factorization I agree, but that you can somehow be randomized at the algebraic.
there's no complete problem for randomized classes, but
We don't know, I mean, well, maybe you're going to say that if you can do this deterministically, then permanent is how?
well, okay, so that's I mean, okay, so that's what I want to say next. So there's also a strong connection between the randomization problem and the proving lower bounds, which is via Arnes. It's the same Arnes versus randomness paradigm that we have in Boolean complexity. So it is known that if you can find, if you have a polynomial, it doesn't have to be a permanent, but okay, it helps if it has some structure. If you have say a multilinear polynomial for which you have lower bounds, then by using an analog of the Nissan-Wieser generator in the algebraic world, you can construct something that's called the eating set, which I will define and solve this question not in polynomial time, but in quasi-polynomial time. And vice versa. If you have an efficient algorithm here of a certain form, then you can get a lower bound. But it's not, I mean, unless, but to solve, I mean.
The lower bound is like next versus something.
No, I mean, no. No.
I
I mean, I didn't plan. I'll say what it. Okay, so maybe first I'll define an eating set, and then we'll discuss those things. Okay, so if you think about the Schwarz-Zippel, the Milo-Lipton result, it's something that you call a black box result. You don't have to know how the circuit looks like. You don't have to see the wires, the gates, the way the computation works. You just have to get some basic information like the degree of the circuit. So, so this gives the following question, which is the question about heat. I mean, it's a new notion called the eating set. For let's say size S. So eating set is a set of inputs such that if C is not identically 0 of size S and degree R circuit, well, but the degree of a circuit, let's call it the maximal degree of intermediate computation in the circuit. Okay? You know, and perhaps for this talk, let's even say that all computations are homogeneous, just to simplify things. And by this I mean that we only care about homogeneous polynomials. So these are polynomials in which all the monomials have the same degree. So without loss of generality, we can just restrict our attention to such polynomials and just make our life slightly simpler. So anyway, so it says that if you give me the parameter, I mean, so H is a heating set if it's a set of inputs, such that whenever C is a non-zero circuit, there exists some input in H such that C of V is not zero. So of course, if you look at the Schwarz-Zippel, the Miller-Lipton lemma, if you just take this huge cube, then it is a heating set. But the point is that a result of Heinz and Schnorr shows that exists age of size polynomial in all the relevant parameters. Okay? And notice this is already not trivial because there are infinitely many arithmetic circuits, right? Because the coefficients come from an characteristic zero field. So it's not that we can apply union bound, just say that, like this is a very, I mean, this happens with, I mean, you can show that this happens with exponentially, I mean, the probability that you fail if you pick age at random is exponentially small, but you cannot take a union bound in the trivial way just because you have to union bound over infinitely many circuits. So it's not a trivial result. It's not that it follows easily just from looking at the Schwarz-Zippel. Look also that I did not restrict the bit complexity of the coefficients appearing in the circuit. Okay? The coefficients can be arbitrary. I mean, I allow you to use transcendental numbers. I mean, so if I were to restrict the bit complexity, then a simple union bound would work. But as we stated it cannot work. So different argument. But anyway, Einstein says that small heating sets exist. And now what follows from Arden's randomness, and that's a result of Kabelnetz and Impaliazzo. Double L or double Z? It's okay. Forget what to multiply. It basically shows that if, for example, let's say permanent requires let's say exponential in n circuits, for example, then this implies that we can construct such a heating set of size at most let's say n to the O of log O, exponential in polylog n. So quasi-polynomial size heating sets. And vice versa. And it's not exactly vice versa, but rather that if age is of size poly NSR, so you have, let's say that we can get a small heating set, then we can find a hard polynomial.
That's already in Alger's paper before.
Yes.
And here you are restricting the bit complexity of it.
Yes, here, yeah. I mean, when I speak about heating sets, I didn't say it, but I will be, so this heating set, for example, each vector has n coordinates, but each coordinate has a small bit complexity, right? If you express the coordinate in bits, it's logarithmically many bits. Here, for the result to hold, I mean, it's enough that you have a heating set where the complexity of each coordinate is at most polynomially many bits. And this hard polynomial, okay, it belongs to some high complexity class. It doesn't have to be in VNP like the permanent or something, but you can just, I mean, the point is that, right, what is the idea? The idea is that you know that if a polynomial can be computed by a small circuit, then that circuit should not vanish on one of the inputs of H. So if you have a polynomial that is not zero but vanishes over all H, then it cannot be computed by a small circuit. So you just solve a system of linear equations to find the coefficients of a polynomial that vanishes on H. So the way you do it, I mean, you don't get the polynomials in VNP. However, if the heating set is a very, very structured, I mean, if you can construct it in a very structured manner, then you may get a polynomial in VNP that's difficult, but it's another restriction on the way that you construct the heating set. So we'll not go there. But basically, the message is that lower bounds and the randomization are very related, also in the algebraic world. But yeah.
So in existential result for hitting sets? Is the degree restriction required?
Yes.
Yeah.
So if I just look at size as polynomials, there may not be a small hitting set?
There should, but we don't. I mean, it doesn't follow from this argument. But there should. Okay, so that's the basics, and so this result is existential, and we know, and so they didn't only prove it; they also showed that a random, right, moreover, that a random age containing this interval of size polynomial of the adequate size is a good eating set with high probability. Okay? Right. So we know that picking age at random gives a eating set. But here's the basic question that we're interested in. So question. So we want to construct age for, let's say, size S and degree R circuits. Okay? So that's a question. So we know that picking age at random works, but I want to be guaranteed that it works. So how do you verify that ages work? How do you, you want not just to know that you're correct with high probability, you want to be sure that you have a hitting set. Okay? So this is one an interesting question. Okay, but actually, in this talk, so we spoke about what eating sets are, what arithmetic circuits are, but there's another word which is the closure of small arithmetic circuits. So let's speak about that now. Okay, so just to know, this is one question that we're interested in. Okay. Okay, so we defined the class VP, which is the class of all polynomial families that have small arithmetic circuits. Now let me define the class that's known as the closure of VP, which is the closure in the usual sense, as we think about taking a set of points and closing it under limits. So what is VP? So let me first give the definition. It's, I mean, let's say that a polynomial family is in the closure if it is the limit of polynomial families from VP. So what do I mean by this? If there exists, let's say, I don't know, G and K, so okay. So K is some index now. So for each K, G and X is a family of polynomials, and we have like infinitely many families such that each family is in VP. So we have infinitely, I mean, we have a collection of families in VP, and such that for every n, if you take those polynomials and take k to go to infinity, you get your polynomial. Oh, okay, so that's maybe, let's forget for a minute about family. Just fix polynomials on n variables. So we want to say that an n-variate polynomial is in the limit of some other polynomials if coefficient-wise those polynomials converge to your limit polynomial. Yes, Tony? No, we don't know. I mean, the verification, it's not clear how to do the verification. The question is the verification, I think.
But you will go back, you will talk about the complexity.
Yes, I'll talk about the complexity, but no, but no. So, I mean, I'll speak a little bit, but the complexity of this, we know that it's in P-space. This question is in P-space. And if you assume the generalized Riemann hypothesis, you can put it in the polynomial hierarchy in sigma 2, but you need GRH for that. Because how do you verify? How do you, let's say that you have H.
The circuit has the coefficients which may be
Yeah, I mean, you have to, I mean, you have age. I mean, I give you age. How do you, what's the verification now? You have to somehow rule out the existence of a circuit that vanishes on that set. And the coefficients don't have small bit complexity. So,
It's like finding a short proof of why it's a good idea.
because, I mean, it's allowed. I mean, it's allowed for them to be arbitrary. Yeah, so, I mean, it's not a realistic model in the Boolean sense, so it's just, that's,
The consequence of fitting set being in PSPACE for PIT is sort of already known, right? Because if you can construct fitting set in PSPACE, then you can do PIT in PSPACE.
Yes.
But that's obviously true because they have a randomized algorithm.
again, depending on the coefficient, I mean, if you restrict the bit complexity, so it's again, it's the same question. It's exactly the same question, right? I mean, if you restrict the complexity, I mean, the discussion about the bit complexity is that we have the circuit, and in the circuit we have constants, right? We call them alpha and beta. If those alpha and betas come from a small set, or they can be described with polynomial linear and bit complexity, then yes, you can put everything in sigma 2. Yes. But no, we allow them to be arbitrary. And we'll see that it's important. When we speak about closure, we'll see that you cannot, I mean, it's really, I mean, we cannot restrict ourselves to small bit complexity. I mean, if we want to speak about closures. Okay, but...
Actually, even the minority or whatever, this is not, strictly speaking, in BPP, this algorithm. If the given circle is...
Or you choose random.
No. The choice is not a problem and the integers is big or small. But it's not a problem for the input. But when you evaluate the circuit, I mean, what's really assumed is that you can evaluate this arithmetic circuit. It's a it's just this black box reduction. If somebody evaluates it, you just want to know if the outcome is zero.
Right, but
to actually evaluate the circuit,
you cannot write down.
Coefficients are described by,
Yeah, I mean, if the coefficients are transcendental numbers, so it's like having variables, and then you basically have to write down something of exponential description, right? It's like, yeah.
So the definition of the limit, can the complexity depend on k of each g and k, or?
No. So okay. So we want to say that. So yeah, it was a bit. So let's say that a family Fn is in the closure of size S and degree R, if. So that's what we'll be interested in. Not about the general closure of VP, but rather you fix some size bound. Let's say n to the 10. Yes. And then if there exist families of, I don't know, G and K, each G and K is size. So S is S of S of n and R. Let's say it's everything. Think about S as being polynomial in n and R as being polynomial in n as size S circuit. Say the circuit of degree R. That's it. Etc. Okay. So we really, so I mean, we speak about families, but let's fix some n, right? We want some polynomial n variables to be the limit of a sequence of other n variate polynomials that each of them is a small arithmetic circuit. And small, it's uniformly small, like n to the 10. But of course, since we speak asymptotically, it has to be family of polynomials, etc. But really you can think about a single n for this talk. Okay, so clearly VP bar contains VP, right? Because the polynomial family is its own limit. So again, when we speak about limit, it's like coefficient-wise, okay? So coefficient-wise. So you don't have to, I mean, you can think about Zariski topology, etc., but just the usual Euclidean topology where you think about each polynomial as a vector of coefficients. So those vectors of coefficients converge to the vector of coefficient of that polynomial. That's the meaning of taking a limit. So yeah, so VP is not closed, and I'll show an example. I mean, I'll not show an example for VP, I'll show some other example. So, of course, so we have that VP is contained in VP bar. It is believed they are different. I mean, we don't have lower bounds, so we cannot prove that nothing. I mean, but it's believed that they are different.
VP bar contained in the entry.
That's a great open problem. The relation between, and I'll say more about it, VP bar and VNP, which again, I did not define VNP. Okay, so I did not define it. But one way to think about VNP, if you don't go, if you don't want to think about, if you don't want to go into more definitions, you can define VNP by a complete polynomial. Okay, that's another way of defining complexity classes, by either complete problems. So you can think about basically about VNP as all the polynomials that you can get from the permanent by substituting linear functions for the variables. So it's like all, again, it's not a very formal definition, but I think it gives a good enough intuition for the class. It's all polynomials that are obtained as a permanent of some linear functions L11 up to Lm. So the parameters here are that you take an m by m matrix, where m is now another parameter. It should be polynomial in all the variables. You want to compute a polynomial on n variables. So this polynomial is, or the polynomial family is in VNP. If you can represent it as a permanent of an m by m matrix, where m is some polynomial in n, where each coordinate is a linear function in your n variables. So that's another way of defining VNP. So the question is whether every family that's in the limit can be described the projection of the permanent. Maybe. I mean, we know that if you restrict the way that in which you can take limits, I don't want to go into it, but you can put several restrictions. Then you can get that those limits are in VNP. But for the general definition of VP bar, we don't know. And it's and actually it can be in VNP. It's not clear. I mean, but maybe it will. VNP, it's not clear that it's closed.
No? If it's closed, then VP bar would be in it.
Sorry?
If VNP was closed, then VP bar would be inside it.
Yes, for example. Yeah.
Why can't you just take like the limit of the permanent?
Because again, it depends on the coefficient. Some coefficient can go to infinity, some coefficient can, I mean, you'll see an example, okay? No, but I'll give an example of something, because to show something is here and not here, you have to give a lower bound, and we don't. The permanent, I mean, okay, in VP bar, I'll show you something else about tensor rank. I'll show you tensor of rank 3 that's in the closure of rank 2. So there are some things where we can show difference between closure and the actual class, but. Yeah, maybe counting argument or something, but we don't. But it's not clear because you have enough degrees of freedom somehow. And, yeah. Yeah. So I mean, we don't know. I mean, I don't know. And
Do you have any kind of upper bound on VP bar in natural?
exponential size.
Exponential is an upper bound.
Yes, exponential is an upper bound.
That's also not.
Yeah, that's not trivial. I mean, you can. I mean, one way to think about. I mean, VP bar. Okay, maybe when we speak about the example, I'll say something about VP bar, about why it's exponential. Yes.
You fix the degree here, right? So everything is in some fixed degree. You can always do that to circuit the sum of monomials.
But is this way. I mean, yes, exponential. But yeah, right. That's a very easy way to see it. No, but the coefficient you don't care. But yes. If you restrict the degree, then yeah, exponential is always an upper bound. Yeah, of course, that's very simple. No, I meant some. I mean, okay. I mean, okay. We'll speak about it soon. But yeah, exponential is always an upper bound.
If you don't restrict the degree, then how do you even know that VP bar only contains polynomials? Right? It might contain things that are not polynomials.
I mean, if you restrict the size, then you get an upper bound of the degree anyways, right? So it always contains polynomials. But okay, but I mean, so we also spoke about the question of showing that permanent is not in VP. All the lower bounds technique that we have today are algebraic in some sense. What do I mean by algebraic? I mean, okay, so we don't know how to prove any lower bound for VP, but there are some restricted classes of arithmetic circuits for which we can prove lower bounds. And these lower bounds, the way that they go is usually you look at your hard polynomial, you put the coefficients of this polynomial in some matrix, and you look at the rank of this matrix or something like that. So this is what I call an algebraic lower bound. So it's like you take some polynomial in the coefficients of your vector, and you somehow argue that this polynomial is not zero on your hard polynomial, but on the other hand, it vanishes over all polynomials that come from small circuits. Okay, so this is how the lower bounds look like the partial derivative methods that I assume many of you saw. I mean, I don't want to, I mean, if you have time and you want to see, I can describe it, but basically says that if you look at the coefficient vector of some polynomial and you put them in a matrix in a certain way, then this matrix will have full rank. But on the other hand, if you will consider a small arithmetic circuit of a certain form, and you look at the coefficients of the polynomial that it computes, and you put them in the matrix in the same way, you will get something that's not full rank. So if you take the determinant of this matrix of coefficients, it will vanish on polynomials that come from small structured computations, but it will not vanish on your hard polynomial. If you think about it, the zero set of a polynomial is closed under limits. So all lower bounds techniques that we have today actually show that some polynomial is not in the closure of some circuit class, right? Because if you have a polynomial vanishing on this circuit class, it also vanishes when you take the limits of things from that circuit class. So all the techniques that we have today are actually for separating a polynomial from a closure of a family of polynomials. And you've heard talks about it, I guess, but so basically the GCT program of Catan actually aims at, I mean, so this is one question, the VP versus VNP. It's not, the VP versus VNP is one question, but here's another conjecture, which is the basis for all the idea to go to GCT, is that the permanent, so this family is not contained in VP bar. And the point is that if we are going to prove that a low bound for the permanent using algebraic methods, then we are actually going to prove this thing. So we might as well conjecture that that's true and continue with looking for algebraic techniques. But the GCT program of Catan that aims to separate VP bar from VNP, right? Because if you Catan and Sohony and Mili and Sohony, yes, Mulmule and Sohony, yes. So basically, if you think about VP as being something and VP bar is like the closure of this thing, then you somehow believe that the permanent is outside. And then you look for some polynomial that vanishes here, but does not vanish here. That's basically that's the way that an algebraic lower bound works. Okay, so VP bar is clearly a more rich family of polynomials than VP. We don't know how much richer it is, but it looks to be richer. It is believed that it contains hard polynomials, but this is not known. So again, so it's believed. So it's conjecture. It's that VP bar. Let me write it like this. It's much harder than VP. Again, I'm not sure how many supporters there are for this conjecture, how many people, but some people believe it. Some people believe that it's not as difficult, but that's one conjecture. And okay. And now you can ask yourself again the question about PAT for VP bar, which is again clearly a much more difficult question because you have to fight many more polynomials. But it turns out that again that the same result of Einstein-Schnorr, exactly the same proof is that a random age is contained in, let's say, 1 to poly n SR is a eating set for VP bar with high probability. So exactly the same result, the same parameters. And the reason is that the way that they prove that a random set age is a heating set is by somehow arguing about the variety generated by polynomial of small circuit complexity. And when you speak about varieties, you speak basically about the closure of the varieties. So the result that they had holds automatically without any effort. They didn't speak in the notion of VP bar, if I recall, but just, I mean, you have to say nothing to get the same result. So we know that there are sets of small bit complexity that hit every non-zero polynomial in VP bar. So this is kind of saying that maybe VP bar is not that more complicated compared to VP. But again, and now if you think about so.
Any hidden set for VP is a hidden set.
So that's a great question. I believe the answer is no. I'll show an example that supports this intuition, but who knows? I mean, maybe. I mean, I don't know. I'll just give an example where a hitting point for a class of polynomials does not hit the limit. But that's not, of course, an example. But okay. But we will speak about that when we speak about the hardness of the question. But if we spoke earlier about the hardness of verifying that age is a hitting set for VP, we said, oh, you have to, the problem is that coefficients can have large bit complexity, etc. Here you don't even know what you are fighting, because the polynomial that you are trying to read does not have a small representation. Or at least we don't know that it has a small representation. Maybe we don't even believe that it has a small representation. So it's a limit of infinite family of polynomials. So verifying now seems a much more harder task. Okay?
There's a page on the floor in case you are
Oh, that's the last page. Okay. No, I just want to make sure that I didn't forget to say anything. Okay. Great. So here's another question. So, okay. So there's a more difficult question. Let's construct H for the closure of size S and the degree R circuits. And this is the question we are actually studying. Hitting sets for the closure of small arithmetic circuits. So that's the question that we'll be interested in. Okay, good.
What's the existence of a small set?
So that's the Einstein. That's this.
I mean, I can imagine how it's done for not a closure, but how does it?
So what is the, okay? So I'll speak about this idea soon. Okay, but I don't. I mean, I'll get to it.
You might have already answered this, but I forgot. The randomized algorithm, does it work for VP bar?
So it's not clear, but it does. I mean, this shows that it does.
Ah, I see.
So.
Okay.
Yeah, but on the face of it, well, it is. Yeah, no. So sorry again. So again, because it's a degree. I mean, it again. I mean, yeah. Because you restrict the degree, then you know that the limit polynomial is also of small degree, and then Schwarzschild works anyways. So Schwarzschild works, but again, taking the union bound now, if earlier you took over an infinite family, now you take about. Yeah. So yeah, of course, but yeah. So just from degree reasons. So this is why also we think that algebraic complexity should be easier than Boolean complexity, because we have the degree bounds. We have, I mean, it seems much more structured. I mean, you have the circuit can fool you in less ways than Boolean circuits. So we should do something about that. Okay. What's the yeah, it's just they're constructing a new building for the CS department in Tel Aviv, and now we got an urgent email that the architect thinks that small boards are much more nicer than large boards that go up and down, and they need to get enough support to argue with the architects. So, so yeah. And what do you think? Yeah. No, it's really, and there are discussions about that, but anyways. Okay. Good. Okay, so let's just speak a minute about this question of verifying the, I mean, so we have a Monte Carlo algorithm or randomized algorithm, just picking an age at random. And there are many other questions for which we have randomized algorithm, but we can actually de-randomize them in PSPACE. For example, okay, I'll just mention a few such questions. Expander graphs that expand beyond half the degree. So, for example, constructing expanders Lossless yeah, maybe that's lossless expanders. So we know that a random graph, random deregular graphs with high probability, if you take a small set of vertices, the neighborhood grows by a factor of, if the degree is d, by at least a factor of d minus 2 or d minus 3. But current techniques only allow us to prove expansion of d over 2. So, but we know that most graphs have this property. So how do you construct such a graph? So either you come up with a construction that the construction itself carries a proof that it expands like this, or you just go over all graphs, and then for each graph you verify that all small sets expand. And how do you do it? You do it in PSPACE basically, because we have to enumerate over all sets. Similar question is like codes on the Gilbert-Varshamov curve. Again, I don't want to go into definitions. So what those of you know, it's like family of linear error correcting codes that satisfy certain properties. We know that random code has these properties. We don't know how to construct them. But in PSPACE, again, you can just go over all codes. For each code, just look at all the vectors in it and check that there's the property. So this thing can certainly be done in PSPACE. Yeah, another question is, for example, coming with a truth table of length n that cannot be computed by circuits of size, let's say, square root n. That's, again, you can do it in PSPACE because you can enumerate over all circuits.
It's all 1 per second, now it's way lower than PSPACE.
This one, yeah, yes. It's way lower than PSPACE, yes. But this question, it's not clear because there's no easy way to enumerate all circuits in your computation. And here it looks even more difficult. However, this problem can be done in PSPACE. Let me just give a hint on how this is done. So the first question, let's say question 1. So eating set for VP can be constructed in PSPACE. And this was observed by Mulmuley a few years back. And basically how the argument goes. So yeah, okay. So just to present the argument in the simplest way, it will be perhaps easier to use the notion of a universal circuit. It's not really necessary, but it just makes our life easier. So what's a universal circuit? So basically, you said that we are interested in size S circuits of degree R. But size S circuits can have different graphs, of computation, right? But basically, a universal circuit is a circuit that encodes all small circuits. So it is some arithmetic circuit of size, maybe now it's polynomial in NSR, not just of size S. And you can think about it as having two sets of variables, x and y's. And the x are going to be the variable of the resulting polynomial, and the y is just like the way to encode a circuit in it. So it tells you, you can, right? I can say more about it, but it's not how to show that you can just take some universal graph that encodes all smaller sizes graphs in it, and the y variables will basically tell you whether you take an edge or not take the edge, whether you put a 0 or 1 on the y, or which coefficient appears on the edge. So if you look, so let's call this circuit psi of xy, and it has the property that it has a small size, and for every c of size s, there exists some assignment, let's say, rho, such that psi of x rho is the same polynomial.
There are no coefficients inside.
And inside psi there are no coefficients.
So the y's, input y's have to be huge.
Yes, the inputs are arbitrary. And they should, in general, be huge. But that's just an easier way of saying, instead of working with all circuits, you can just think about hitting all polynomials of this form. So this can compute more polynomials than just size S circuits. You have more freedom here. But for our purpose, just think about this circuit. Okay, so we want to verify that we want to construct H in PSPACE. How do we do that? So Einstein Schnorr told us that this H exists in some small set. So we can try to enumerate over all sets H. And then given a set H, you have to check whether it's a heating set or not. And that's the hard thing. So what does it mean that age is not eating set? So let's say that age is not eating set. What does it mean? It means that there is some small circuit that is not zero, but vanishes on all the points in H. So it means that there exists small c such that, first of all, for every v in H, c of v is zero. But since we speak about homogeneous polynomials, we can also say there also exists some input on which c on that input equals 1. Right? Because of homogeneity, whenever you're not zero, you can rescale your input to get any value that you'd like. So it means that H is not eating set if you can satisfy this. But what does it mean? It means that there basically, so you can write it down as, I want to write it here. So basically, you're asking yourself, does there exist a row and an alpha such that psi of v row is 0 for every v in your set, and psi of alpha row is 1. So you can think about it as a set of polynomial equations, right? Each v in your set defines an equation in the row. Think about the row as unknowns now, and also about alpha is unknown. So this is a set of size h many equations, and that's another equation. So you basically have to check whether a set of polynomial equations that are defined succinctly, right? Because this psi is a small circuit, as a solution. So this is called the Null-Steinsatz problem. We are giving a set of small arithmetic circuits. We have to check whether they all have a common non-zero solution in this case. Okay? And this can be solved in PSPACE. It's a non-trivial result, but it can be done in PSPACE. So that's in PSPACE. So that can be solved in PSPACE. Yeah, there are no coefficients.
No, here is 0, 1 coefficient.
But is it true that, sorry, I guess I'm asking a question. So is it true that such a witness, there must be some upper bound coefficient?
Yeah, there's some I mean, on alpha and rho, I mean, on what? On rho and alpha?
No.
It's doubly, yes, doubly exponential.
Right, because you can write them down.
It's exponential.
Double.
No.
Oh, the length is double or the sum?
The length is
Lang-
exponential. That's maybe exponential. No, it's
No.
something else.
Rho can probably
Yeah.
be transcendent in
No.
No, you don't need
Knowing
transcendent.
the coefficients of the other circuit.
Again, so H is very explicit, and rho and alpha are unknowns. These are the variables in your equations. So basically, you can asking whether there exists a solution to that system, right? You're asking about x and y, whether there exists. Yeah, and it's a very clever algorithm. It's by Kani. It was done, I mean, he's a robotics person. And in robotics, right, if you think about the arm movement of a robot, it's like a set of polynomial equations, and you want to know things about them. So the fact that you can solve polynomial equations in PSPACE is very important. And in fact, we'll need much more from Kani, but we'll get to it later. But
Is it probably hard for that class?
yes, Null-Steinsatz, I think, I'm not sure. I mean, whether Null-Steinsatz is complete for PSPACE, I don't know. No, actually, no. So we actually, and I mean, in Koiran, maybe I'll write it.
I mean, it's the complete problem for the extension theory of the field. It's not known whether it's
No, not even, not
It's
this.
much easier because
Yeah, that's easier. I will speak about the existential theory of the real soon, but that's, so basically, Koiran actually proved that assuming GRH, this Null-Steinsatz, so this question of can be done in the polynomial hierarchy, and in fact, I think even in sigma 2, maybe. I'm not, but that's assuming GRH, because basically you reduce this question modulo many different primes, and you show that if you solve it, if it's a solution for enough primes.
Then it does boil down to the fact that I can bound the coefficients to be able to do.
yeah, it does boil down.
But,
So
but
it's
you-
not GRH, not the full GRH. There's the result of Odlisko and Lagarius saying the 0, 1 coefficient, just like this. Then there is a prime, so this over C, but the coefficients are 0, 1. Then there is a prime, which is just of polynomial size, the polynomial in many bits. So that if there is a solution, there is a solution when you reduce, over this finite field, basically.
Right, but that's but you need something. I mean, it's not.
Yeah, I'm just saying it's a consequence of GRH,
Yes.
but GRH is a
Yeah, of course.
number. It's something.
Yeah, no, of course, but yeah, but that's the best we know.
Open to prove this, given anything better than PSPACE under your assumption?
Yeah.
Yeah, I mean, I don't know. I mean, would it imply anything on the other direction? I mean, okay, if you prove something better, it will show that, I mean, if you show that it's not possible, it will show that GRH is not true, right? But if you show that it's possible, it will, I mean, you expect it, right? Because you expect consequences of GRH to be true, so.
But it doesn't use Kern's upper bound.
This, no, that's, this is a, no, this, yes.
It just says that if a system of polynomial equations
Right, yes.
implies, of course.
Yes. Okay, so this is the situation for this. But now let's go to the question of, okay, let's say that we can construct a 18 set for VP. Let's see what's the problem of going to VP bar. Okay, so let me try to give an example showing that VP and VP bar may be different. This example will actually speak about the tensor rank. So let me, so it's, okay, it's only 1 hour, okay. Let me just see if I wanted to say something more. Okay. Yeah, so let me speak about tensor rank. So let's look at a specific tensor. I'll first write it and then define what tensor is. So we look at a very simple tensor. It has 6 variables. And it's actually a tensor coming from polynomial multiplication. Let's write it down. So it is some polynomial in the x, y, and z variables. It is this tensor. Okay. So basically, if you think about the x variables and the y variables as being coefficients of linear functions, so it's like x0 plus x1 times some formal variable a. This is y0 plus y1 times a. And this is what you get when you multiply these two polynomials modulo a squared, right? You just get the free coefficient and the linear part, okay? So this is something that we call a tensor because, I mean, you have the variable are partitioned to 3 disjoint sets, and each monomial involves one variable from each set. And we can define the notion of a tensor rank. What is a rank 1 tensor? So a rank 1 tensor is just a polynomial of the form some linear function in the x variable, some linear function in the y variable, and some linear function in the z variable. Okay, so that's a rank 1 tensor. And the rank of a tensor, so rank of t, is the minimum, let's say it's the minimum size S such that you can write t as a sum of rank 1 tensors. Okay, so that's some complexity measure.
The variables in each of the linear forms have to be disjoint?
Yeah, these are the x variables, these are the y variables, these are the z variables. It's like, like the determinant is a tensor, right? Because you have the first row, the second row to the nth row, and each monomial contains exactly one variable from each thing. But the best algorithms that we have today don't treat it as a tensor, so they don't, because the rank of that tensor is huge. They do something else. But anyways, we can restrict our attention to tensor rank. It's a very important measure. The question about computing matrix multiplication efficiently is equivalent to the question about the rank of the matrix multiplication tensor. You can represent matrix multiplication as, I mean, for each output associate a new variable zaj, and you can write the tensor. Okay, so here are some facts about this tensor, and that's like an exercise that you can do on the break, if I'll give you a break. Do we take breaks, or? We do, okay, so after this, maybe we'll take a break.
Exercises need a break.
No, you can solve it while I'm speaking. So the rank of this tensor is 3. Okay, that's, I mean, you can just prove it. I mean, of course, if I write it like as a sum of monomials, it has 3 monomials, but it says nothing, right? because I mean, a rank 1 tensor can have many monomials. But you can prove that the rank is it's at least 3 and it's at most 3 because you have a trivial representation. Now let me show to you that T is in the closure of rank 2. Okay, that's what I want to show. Okay, so here's the rank 2. So let's have a new parameter epsilon that will eventually take epsilon to 0. So think about epsilon as being the k earlier, but now it's like 1 over k. And what would be T epsilon? Yes, I think it's correct, and if it's not correct, then I look at my notes. So let's see what's note. I can look at them. Yeah. Okay, so what's going on here? So let's open the brackets, and you can do it, or you can trust me that what you get when you do the computation. So you get the x0, y0, z1 times 1 over epsilon, but this is cancelled in the second term. And then you get x0, epsilon, y1, z1 times 1 over epsilon. So you get basically this term. The second product gives you x0, y0, z0. So basically you get t. But then you have another term that comes from the x1 times 1. So that's plus epsilon, x1, y1, z1. So that's what you get.
Yeah, but only 1 epsilon.
Yeah, because of the 1 over epsilon. And just so look at it. I mean, the resulting polynomial is everything is like that's your original tensor, and you have a small coefficient. And certainly, when you take epsilon to go to epsilon to 0, this goes to t. So t is in the closure, right? Because you have a family of tensors. So if you take the coordinate-wise limit, coefficient-wise limit, you get t. But look at the circuit. So it's rank 2. But all the coefficients belong to some coefficients go to infinity, some coefficients go to 0. But when you open the brackets at each specific t, things cancel out. But I mean, you cannot avoid this in some sense if you want to take limit. Because if you restrict the bit complexity of your coefficients, then you can take the limit inside your universal circuit somehow. So you see, I mean, we spoke about universal circuits. So if you can ask yourself, let's say that some polynomial is in the limit of some other family of polynomials. So each polynomial in the family has a small universal circuit. So the only difference between different polynomials are the y variables. So if all the y variables belong to some small set, to some compact set, they were all bounded, then you could take the limit here. But the problem is that for things to get interesting, you need to have coefficients going to infinity and going to 0 and cancelling out. So that's why, I mean, it's not clear what's the relation between VP bar and VP.
It's probably good to give Strassen credit for making this up. And,
yeah, so Strassen was the one speaking.
This started GCT 30 years earlier than
Yes.
normally and so on.
Yes.
So on that note, could it, for the matrix multiplication tensor, could the rank and the border rank be different?
So no. But that's because of very special properties of matrix multiplication, because it has another underlying structure. But no. So for matrix multiplication, it's known that it's bounding the border rank or bounding the rank. It's equivalent because there are tricks. But that's a very special tensor.
Not that the rank, the border rank are the same. The
No.
exponent is the same.
The
border rank can be different.
No, but it cannot be much. It can be larger, but some constant factor, but not in the limit.
He was asking.
Yeah, I mean, for every specific n, there can be a difference. But if you think about the exponent, I mean, it swallows up. Yeah,
This is also a special case of the fact that by geometry that the image of a polynomial map is not variety.
Right. It's exactly this, because the set of all small small.
Yeah, that's what the border rank is.
Okay, I'll say in a minute. I'll just answer. Okay, so yeah, the set of all small polynomials are exactly the image of this map under all assignments to y. Actually, it's even a larger set, but that's an interesting set for us, and it's not closed because of reasons like that. Okay, so that's why it's harder to speak about VP bar, and it's not clear that they have a small representation. But exactly. Now, Tony's question: what's the border rank? So you can, you can think about matrix multiplication as again a tensor that, right? The tensor associated with matrix multiplication. It's basically the trace of x, y, and z, where these are all n by n matrices. Okay, so this is one polynomial. Each monomial involves, and you can ask about the rank of this tensor for n by n matrices. And you can also ask, what's the border rank, in the sense, what is the minimal rank R, so that this tensor is in the limit of rank R tensors. So you get, so you have the rank. You can ask about the rank of this T, or you can ask about, it's usually denoted like this, the border rank of T. So it's known that this is always smaller or larger, and there are examples where it can be strictly smaller. Like I showed you one tensor like that. However, for matrix multiplication, because it has the property that multiplying n square by n square matrices can be seen as like a tensor product of tensor of multiplying n by n matrices, you can somehow take this representation and leverage it to somehow get to prove that the rank of a larger matrix multiplication tensor is better than what we would get by just tensoring this simple representation. And the way that it affects the exponent is just, it does not affect the exponent of matrix multiplication, basically. So if you can prove that this thing is a small exponent as a function of n, then the same exponent holds 0, and you lose a constant factor. That's it. Right, so I think maybe that's a good time for a break. So what have we done so far? We stated the question. We showed why it can be difficult. Maybe here, let me just say a word. So we saw that t is the limit of t epsilon. Just see what happens when you look at t of this input. 0, 1, 0, 1, 0, 1. Okay, so it's basically the linear function a times a. So you know that you work modulo a square, so it's like 0. But when you plug it to t epsilon, so t vanishes, but this gives you epsilon. So on this input, you can just check. Although t vanishes, but t epsilon is never 0. It just gets the value epsilon on that input. So you have a point that hits all the tensors here. It's not all rank 2 tensors, but all those tensors, but the limit vanishes. Because, again, a set of non-zeros can converge to 0. So that's the point. That's why it's not clear that the eating set for VP will give you eating set for VP bar. So I don't have any formal claim like this, and maybe it's true that the eating set for VP gives the eating set for VP bar. I just don't know. But there are, it's not clear that it's not obvious that it's old, so there's something to prove. Anyway, so let's take 5 minutes. Okay, okay, so let's continue. So we understand the question. Let me say a word about it. So we know that the first question, we saw that it can be done in PSPACE, right? And we explained that how you do it using null-Stellensatz. So in the same paper, where Ketan noticed that it can be done in PSPACE, he also noted that this question of constructing a eating set for VP bar can be done in exponential space, which is, again, it's not immediate, I think.
Well, exponential upper bound for the circuit size, which is trivial by what Zev said.
But what is the polynomial that you get? How do you compute the limit?
The limit is a polynomial in which
No, so constructing a small set H. You want to construct a small set H that will lead all polynomials of small limits. So, yeah, so, right, so, yeah. There is an exponential size circuit, but there are no small eating sets for exponential size circuits.
So that you can find the annihilating polynomials.
Exactly, so that's what you do. Basically, you say that the image of all small polynomials, some variety, and basically you compute a Grabner basis for the polynomials defining those variety. I'm not going to go into this, and if you don't know the notion, don't worry about it. And once you have the Grabner basis and you have your set H, you have to check the intersection of all the polynomials vanishing on your set H, and to check whether the only polynomial that vanishes over all H that is in this set is a 0 polynomial. So it involves some computation on Grabner bases. And Grabner bases require exponential space. I mean, it's known that they're complete for X space to compute. So if you go in this direction, no? Yeah.
Just confused because it's exponential of degree, right?
Yeah, so so what you need is exponential in, so you need to be exponential in the host dimension, in the dimension of the thing. So the dimension is polynomial, so it's exponential in this. To be exponential in the degree. You don't have coefficients here. You don't have coefficients, yes. So yeah, so you can, using Grabner basis technique, you can put it in X space.
By what Zev said again, I mean, you know a small heating set exists, you just want to verify it.
Right.
But then you just have to iterate over universal circuits which have exponential size.
But it's not clear that it will be a heating set there's no small heating set for exponential size circuits, right? There's no
That exists. So we just have to iterate over this and then verify.
But the exponential size circuit can vanish over this and it will not say anything, right? There are too many polynomials in exponential size. It's too large family. This is also a larger family, but it's not too large in some sense. That's the difference. Okay, so it's known that it's done in X space. And the reason that Ketan was interested in it is because he studied the algorithmic questions in algebraic geometry. And one of the important questions that he studied was something that's called the Netter normalization lemma. So I can just say a word about it. So look at this circuit, right? It's a circuit computing some polynomial of degree r in n variables. So if you think about it as a vector of coefficients, so there are exponentially many coefficients. So the image of this map lives in some exponential dimensional space, right? I mean, the space of all coefficient vectors. But as a variety in this space, it has low dimension because it's defined basically by a few equations. So Netter normalization lemma asks, given a small dimensional variety in a large space, somehow map the variety to a smaller dimensional space in a way that will be one-to-one in some sense, like almost one-to-one. And this question, I mean, so it's a nice result of Ketan, it can be reduced to the question of, I mean, if you have a heating set for VP bar, so basically the mapping, I mean, the way to reduce, I mean, so you want to represent this huge polynomials that live in very large dimensional variety in a small dimensional space in a way that will be one-to-one. And how do you do it? You just evaluate those polynomials on your heating set. Just notice that if you have a heating set, then any two polynomials evaluate a different value, right? Because if they have the same evaluation vectors and you take their difference, then this is a polynomial that vanishes on the heating set. So if the heating set hits a circuit of size twice the size of the circuit computing the polynomial, then this cannot happen. So a heating set for VP bar gives him a map that maps the variety of VP bar to a small dimensional space. And if you can do this, then of course it gives you a leverage. I mean, you understand you can do stuff, right? So that's why he was interested in the question of constructing heating sets for VP bar. And his paper basically was more general. It studied varieties that are called explicit varieties and showed that for them too, there's a randomized Monte Carlo algorithm, basically much in the spirit of the Einstein result, that allows him to get a normalizing map efficiently. But to do it deterministically, I mean, the way that he did it was by referring to this question. So that was the motivation for Ketan. Okay, so that was, I think we now understand the question, there's some background. And the main result that I want to talk about is that we can do this also in PSPACE. So that's the main result, so this can be done also in PSPACE. Okay, so that's the main result of Michael Nye. So now we understand all, I think, the words in the title. I didn't define PSPACE, but I mean, please ask. Basically, just the amount of space we need to be in the input size. Okay, great. So now I'll show how to do it. And, okay. So yeah, so I mean, Ketan noted that it's an exponential space, and using GRH, he put it in exponential hierarchy. We can do it in PSPACE, which is of course contained there, but we don't know how to do better. And you'll see why. It's a difference between solving a system of equations and solving a system of polynomial inequalities. So that's, yeah. So, for example, the problem that we so the problem that we saw here was that we had a limit, and we had a point that got a non-zero value for every polynomial in the sequence, but the limit polynomial vanished on that point. The reason was that the set of evaluation, right, the t epsilon of this input was epsilon. So the values went to 0, the evaluations. If we had another point on which you could prove that all t epsilon evaluates to at least, say, half, then also the limit polynomial would evaluate to at least half, right? So this led Michael and I to the definition of something that we call the robust eating set. So we say that age, now we need some notion of measure. So let's say that it's in, let's speak over the reals, but it's complex too, is an, let's say, epsilon robust eating set for size S and degree R and n var. If for every, okay, C of size S, degree R, and n vars. And now we replace the, earlier we just wanted the circuit to be non-zero. Now we also need some normalization, such that, I'll define this soon, but some norm of the polynomial. And let's define this, I'll soon define this norm. Let's say it's 1. Otherwise, what I say, has no meaning, and we must take normalization. So think about it as some norm, like the L2 norm of the coefficients. You can move between norms quite easily, but I'll define a different norm, but it doesn't really matter. So it satisfies some normalization. So the set is epsilon robust for any such C. Think about it as just saying the coefficients of C are not too small. Okay, just some way of thinking about it. It holds for every such C, there exists some point in our set such that C of V evaluates to at least epsilon. That's the thing. Just the evaluations are not too small. And what is the norm that we define? Again, you can define basically any norm you want, and you can move between them, maybe with some exponential loss, but for us, exponentials will be okay because we work in PSPACE. So basically, the norm that we define, we work with, but it's not very important. You can basically define any norm you want. Well, the measure that's it, it's the uniform measure on this minus from one end to then. Okay? But this is one definition of norm. Another definition of norm is like the norm of the vector of coefficients or the L infinity norm of the vector coefficient. And all those norms, you can show that they are related. It's like, it's not very difficult. Okay, so this is just some definition of norm just because it will be easier to state non-theorems about this norm immediately. But again, just think about it, some normalization, that's not very crucial. Now, what's the point? If we have an epsilon robust eating set, the point is that, now notice that such if, and here's an easy claim, that if H is epsilon robust for size S, for any class, for some class, then it is epsilon robust also for the closure of this class. Why? Because when you take limits, you know that at some point all the norms will be very close to each other because it's pointwise, right? So and that's a continuous function. So from some point on, you can assume that all the norms of all your polynomials are between, after normalization, say between 1 minus epsilon and 1 plus epsilon. And therefore, for each of them, there is a different v on which it evaluates a large value. But since you have an infinitely many polynomials, there's a subsequence that for the same v, all of them will evaluate to a large value, and therefore in the limit we'll also evaluate a large value. Yeah, so we know that, right, let's say that now you have fn, let's say that you have gn going converging to v. So for every gn, gk, let's do like this. So for every one of those polynomials, there is a different input from age on which it has large value. But age is finite, so a subsequence, so there's a subsequence such that gki, such that this is at least epsilon. And therefore also f is at least epsilon. I mean, the reason that it's the same epsilon because, I mean, the norms get very close to each other. So, right, so once you have an epsilon robust heating set for VP, then, or for size circle, then it's also epsilon robust for the closure. So our task will just, I mean, so now what we'd like to do is to, so we have I mean, we want to construct a heating sets for VP bar. Instead, what we'll do is we'll construct an epsilon robust set for VP, or for size circuits. And then we'll be guaranteed that it works in the limit. But now here's the question, I mean, do such sets exist? It's not clear. It does not follow from Einstein-Schnorr, for example. Because there it's just about solving equations, whether something is 0 or not 0. It doesn't say anything about the size of it. So our proof actually has two parts. So 2 questions. So question 1, which is the main technical difficulty in the work, is the small robust. And this epsilon also cannot be too small because we somehow need to work with it. It should be exponentially large in the sense that it's at least 2 to the minus of some polynomial. Okay, so it's not just about maybe epsilon robust set exists for doubly exponentially small epsilon, but we need epsilon to also not to be too small. So do small epsilon robust sets exist for size s, degree r circuits? So that's and remember that epsilon is at least some exponential in minus polynomial in all the parameters. So this is the epsilon that we need a thing to work with. And the second question, which will turn out to be easier, it's a very, I mean, once we have the construction problem, find in PSPACE, and then find such age in PSPACE. And for this, we'll use the existential theory of the reals, but that's a bit later. But first, let's speak about this question. So this is basically the main core of the paper, the main technical difficulty. And actually, I think, I mean, I didn't do that, but that seems like an easy exercise, basically to go over heating sets that we know today for certain classes and turn them into robust heating sets. I mean, I didn't check this, but I have a strong feeling that this can be done. And then it will give you something also about the closure of those families. But yeah, I mean, maybe you want to give your students this as an exercise. Or maybe.
There's a black box way of taking a heating set into a robust one.
I think you can basically by some interpolation tricks, but yeah, so that's the solution, I think. Right, if somehow you are, yeah, you think there's a, I mean, at least for the classes that we know that are so restricted, it shouldn't be that difficult. Okay, so what are the ingredients? Okay, so an epsilon robust heating set should satisfy that every non-zero circuit of that is normalized gets a large value on at least one input of the set. So first of all, you'd like to say something like a random set should have at least this property for a given polynomial, right? We have to take union bound, etc., but we have to say this.
So the set of polynomials with norm 1 is compact, right?
No.
Sorry, not the intersection of this set with the.
Yeah, because again, you saw this T epsilon. I mean, they all have small norm.
The
No, not the circuit, but t epsilon itself. It was t plus something epsilon times another monomial, right? So all the norm was roughly the same. But right. Yeah, I mean, I don't know how to say that to get all the polynomials that have small norm in the closure of VP can be represented by small arithmetic circuits. I mean, that's not true, probably. Right? I mean, maybe it's true if VP bar equals VP. But, okay, so what are the steps in the proof? Okay, well, so the first thing we are going to, yes? No problem.
Sorry. So you said that that result of Corona, whoever it was, already showed that there, existentially, that there's a hidden set.
Assuming GRH.
Oh, that was just
GRH.
Yeah. He wants without.
So we don't have anything except even
X place was the best known.
right. So that result, that doesn't assume George, but
No.
that doesn't give you epsilon.
No, it doesn't. I mean, it did not have the notion even of. I mean, yeah, just.
That argument is somehow.
So we don't know. I mean, I don't know how to verify whether. I mean, that result of Mulmula has the advantage that you give it an age, it can tell you whether it hits VP bar or not. I don't know how to solve this verification problem. I can construct. I can solve the verification problem for an epsilon robust set in PSPACE. There's a different, I mean, there are two questions. One question is construct age that eats VP bar and find it, construct in PSPACE. So,
The finding part, the argument that it's
so the,
exists.
so it exists? No, so,
The argument that they exist for VP bar, that argument also works for epsilon robust, just the existence.
no, we don't know. No, I suppose that's a technical core of the paper. Yeah.
So somehow there's something about that.
Yeah, just because, I mean, usually the proofs speak about dimensions of variety and checking whether what you get is 0 or not. It doesn't say anything about sizes. And it works for unordered field. I mean, I have to work with characteristic 0. So it's very different. But again, you can also ask a slightly different question of verification. Given an age, check whether it's a rating set for VP or for VP bar. I don't know how to do it. Using Grabner basis, you can do it. What I can do is that answer the question of whether age is an epsilon robust. But that's the question too, so that's a different thing. But the existence is the main thing. Okay, so what do we do? The first thing we use is use the anti-concentration results for polynomials. So basically those results show that when you pick input at random, even if you discretize the space, etc., and take your input with poly-size bit complexity, the probability that it will be very small is small. Okay, so with high probability, when you pick age at random, for a given polynomial of norm 1, with exponentially high probability, it will evaluate to a large value in at least one polynomial set. So that's the first thing we need. I mean, I'll state all those results later, but it's basically taking a result by Carberry Wright and discretizing it.
Carberry Wright works on Gaussians, and you want.
It works for any measure that has some property. It's not just Gaussians. Any convex. I mean, it works in many settings, especially also for the unit. But also Gaussians is okay. And in fact, you don't even need this. You can just take some discretized version of Schwarz-Zippel and prove it. I mean, there are many ways of proving what we need. But that's one way to do it. And okay. But the problem is that it only gives for one polynomial. And remember, we have, infinitely many polynomials. So a very natural thing to do when you have such questions is to take epsilon nets. Right? Let's look at the space, the set of all easy polynomials. Let's say that you can find an epsilon net there. What do I mean by an epsilon net here? It's a set of polynomials. Right? Think about it as the image of psi. Right? The universal circuit. So that's the image. So it's the image of psi. Basically, it's this set. So that's inside like R to the whatever n plus R. Whatever. This is the dimension because it's like all the coefficients, and you have degree R monomials in n variables. Basically, this is the number, maybe -1. Whatever. So it's a set of vectors, and inside that huge set, you want to take an epsilon net. What's an epsilon net? It's just a collection of points, so that any other polynomial will be a distance. Okay, maybe epsilon is overloaded of some delta from some other point in your set. So, so we want to work with epsilon robust, and the epsilon we will work with, so anti-concentration results, so it's like with high probability for age random, like C, a given C will be V, be at least some exponentially minus, NSR. Yes, whatever. So epsilon is polynomial, exponentially small, but it's something. Okay, so you need this delta also to be exponentially small, because you have to be very careful, right? I mean, this polynomial, evaluates to at least something exponentially small. You want to claim that if this polynomial is close to one of your things in the net, so it should be close enough so that even when you lose from the distance, you'll still get value at least, I don't know, epsilon over 2. Okay, great. So second idea is to construct or take a union bound. That's an idea right now. That's just, it's not something that it's so easy. Union bound over some delta net. And delta will be exponential much smaller than epsilon, but still everything will be exponentially large. Okay, now what's the problem? So, yeah, don't wait for the rest of the class. Yes, so it's applicable. I mean, so the dimension of the space is exponential. Okay, so we have some variety in some. I mean, usually when you take, if you work on some, let's say, R to some capital D, and you want a delta net. So again, so you have to take the sphere, let's say the sphere inside this, and you want to take an epsilon. You need some compact set or something. It will be basically something like this. It has to be exponential in the dimension.
The dimension of the variety you're interested in is polynomial.
Right, but they are just, it's not enough. But let me continue. So the host space is exponential dimension. Okay, and this is also exponential. But in any case, what you get from here just by applying usual epsilon nets, you get a doubly exponential size of the epsilon net, of the delta net. And then the union bound will fail because this is only exponentially high probability. So it will not work. And now we say, but my variety is a small dimension. So it should be, the epsilon should be in the dimension of the variety. That's not enough. And let me explain why. Just think about something like this.
It depends on the degree and the dimension.
Okay, now you're getting there. But let's speak about manifolds. I mean, intuitively, if you have a manifold, let's say of dimension 2, it should behave like a subspace, and therefore the epsilon net should be like 1 over delta in the dimension. But the problem is that, you can have like very curves filling the space, right? Whatever dimension is. So you cannot just use dimension. But the point is that we are dealing with algebraic varieties. And there's a notion of a degree of a variety, which basically tells you how many such loops it can have. Like the degree is basically, if you take a subspace and intersect it with your variety, how many points can be on that subspace, in some sense, or I mean, for like subspace in general location of the right dimension. So what we prove is that the following was something we needed. I mean, we didn't find it in the literature, so we proved it. But I mean, here's a theorem. Okay, so what's the notion? Okay, so I didn't define what's the meaning of degree. Okay, so degree is basically this. And what we're going to use is a theorem by Heinz and Sivkin, basically, that show that if you look, let's say, the image of psi, this variety, and you look the closure of this variety, so the dimension. So let's call this variety, I don't know, the variety of psi. Okay, so the dimension of this variety of easy polynomials, so let's call this variety V psi. So the dimension of this thing is exponential in your parameters. So it's polynomial in your parameters. And the degree of this variety is exponential. Okay? So the degree, because it's an image of a polynomial map that has small degrees of freedom, a few degrees of freedom, right? Only the x and the y variable, so it's like only s plus n or poly sn degrees of freedom, so it has small dimension. And the degree, we'll later see an explanation why the degree is only exponential. It can be...
If you have an image of polynomial map, the degree
Okay, so that's one, yeah. But yeah, there are exponentially many coefficients, and yeah, so
No, for
No.
the number coefficients.
no, you have the dimension of the space is exponential.
So the number of before the image.
No,
Oh,
it's like the defining equations, but that will be basically. I mean, we'll see anyways. But these are two parameters.
Exponential to the power of n, right?
Yeah, so it's exponential. It's not. So they proved like better better quantitative results, but that's enough for us. There's some polynomial bound on a degree, and some exponential bound on some polynomial bound on the dimension, and some exponential bound on the degree. And the theorem is that if v is of dimension d and degree capital D, let's say, then there exists a delta net of size. So the bound that we prove is basically something like this. V is inside, let's say, R to the capital N, where you have. So we prove something like this for, let's say, V intersect, I don't know, let's say 0, 1 to the capital. Right, you just have to put something in some compact space. So if you just look at all the intersection of your variety with some cube or some ball or something, the size of the dating set is going to be basically 1 over delta to the dimension, which is what we would like. And the way that you pay for all those curves, I erased it, but you remember, I mean, one of the problems was that things can look like this, is that you have another linear factor in the degree, which is intuitive, right? Because you find epsilon at here, and then you can have at most, I mean, that's a very rough intuition, but that's how things look. So this factor can probably, maybe we don't need it, but it's not important. But the point is that if you look at it, everything, so this is size, in our case, so for our psi, it is exponential in all the parameters. Because this polynomial, this is exponential, but that's okay. This is exponential, but that's okay. And this is exponential, but it's outside. So everything is of exponential size and not doubly exponential. Now you can do the union bound because you just need to, I mean, okay, you have to be careful here because you have to make sure that epsilon and delta things work nicely together. But the point is that you fix epsilon in the epsilon robustity to be some small exponential. You then take the delta of your delta net to be a much smaller thing, so that to allow things. Then you get the size of fitting set of some exponential size. Then when you pick h, you just pick enough points so that the probability that you fail will be an exponential much smaller than what you need for the union bound. Right? So, I mean, everything, you have to be careful about how you do things, right? I mean, the epsilon robustness, you do it for some small epsilon. You then take a delta net for an exponential that is much smaller, but that will allow you to claim that every other polynomial here evaluates at least epsilon over 2. Then you know that there is an epsilon net of that size. Now to do the union bound over here, you just say, okay, I just have to sample enough points at random. Carberry Wright will tell me that I fail each time with only a small probability. So if I take polynomially enough things, they will beat that exponential. And then you can do the union bound. And that's basically the proof. Okay, so that's the proof of the existence of the thing. So how do you prove this theorem? So I'll just say a word about it, not more than that.
The results like this that are known, like on the volume of an epsilon neighborhood of a variety in a ball, just things like that.
Maybe, I mean, I searched for epsilon nets in varieties and I didn't find anything.
Epsilon net is the volume of an epsilon neighborhood
Okay.
of a variety.
Okay, so, but the volume will tell you what you need.
Big ball. If it's a vertex there, that's something.
I mean, I don't see why it implies an epsilon net, but maybe, I don't know. But, I mean, yeah, maybe. Maybe it does, I don't know. I mean, I don't know what to say. So how do you prove this thing? So, I mean, the idea is to use induction on the degree, basically. So what we have is like, we have our variety, and what?
No, something, well, we can discuss it later.
Okay. So basically what we do is basically, I mean, we take a grid of, I mean, so that each cell is very small. It's like, this is like delta over something, I don't know, delta over 2 or whatever. And we just look at the intersection of our variety with those things.
So what is the picture? That's the.
So I want to explain how to, just to give the high-level idea of this. So this thing is that this is the variety, and now I'm just taking axis parallel subspaces of codimension 1. So, and there I take them so that this distance is very small. I don't know, something.
Maybe I'll say something that can help Tom. So here's the Schwarzschild lemma. Take a grid, right? Just back to the normal Schwarzschild lemma, and take a grid of with polynomial, right? It's just so it's k to the n, right? K points in every dimension, k to the n. If you have a low degree polynomial, the number of grid points it will go for is at most, 100, 1% of this grid.
So actually, that's another way that we can prove this anti-concentration by some argument like this. But we just apply
So
the.
what is going to prove is an analog of Schwarzschild, where you don't ask how many grid points are you going to intersect, but actually how many cubelets you are going to intersect. And that's
No, you can intersect all cubelets. It's not the variety can intersect.
not the variety, any polynomial.
I'm not looking at this. I'm not looking at polynomial. No, that's not exactly what I'm doing. But what I'm doing, I'm taking the variety of small polynomials, and I just want to reduce its dimension in some sense. So I'm looking at subspaces that are axis parallel, just for its simplicity. So it breaks the space into cells, and all the cells are very small. So because the cells are small, like if your epsilon net contains a point here, then it's close to all the points in the cell, just because the cells are small. And now I look at the intersection of the variety with those things. If I pick the grid in general enough position, then the variety loses one dimension when I restrict it to this subspace. And then you can prove by induction that there is a small epsilon net there.
What then?
Dimension of the variety. Because this is a codimension 1 subspace. So if you take it in general position, it will lose one in the dimension. So we have to be careful because maybe the axis parallel are not good enough for us, but you can rotate things a little bit and it will be good enough. Then you just do induction and you get something. And the degree, the point is the degree is like, you look at, so the degree does not increase, but now you can ask, but maybe you have many disjoint things like this that don't intersect. And then from each one of them, you also need to take 1 point to get an epsilon net. But the point is that irreducible varieties are connected. So each such component will be, it will be part of an irreducible component of your variety, and the degree of your variety is the sum of degrees. So you do also need induction on the degree. That's why you get linear in the degree. That's a very high level, but basically it says that some inductive argument works. Okay, so you just want to do the induction on the intersection with those affine subspace, but maybe some components of the variety, it's not, maybe they are like isolated. So they're contained in your cells. And then if you don't have intersection with the boundary, you need to take a point from inside. But you want, so dimension degree, yes. Yeah, yes. You basically, you just study irreducible component. It's enough to prove it for irreducible varieties, and when you do the induction, you just claim about each irreducible component separately. But that's how it goes. It sounds more complicated than it. You just have to come up with the right idea. That's it. But that's what we do. Okay, so this basically, I didn't state Cadbury right. Cadbury right basically says that if your polynomial is normalized in this way, then the probability that you get value smaller than epsilon is epsilon to the 1 over the degree of the polynomial. So our epsilon is exponentially small, so epsilon to the 1 over the degree will be at most 1/2. So if you pick age of size polynomial large enough, then you will beat the union bound that you get from the epsilon net. So this answers question 1, the small epsilon robust set exist. And now we get to the second question. How do you check whether something is a robust set. And here we need to use the existential theory of the reals. Maybe I'll do it here. So we somehow would like to express the condition of not being an epsilon robust set using a set of polynomial equalities and inequalities, and then check whether this system has a solution. So basically the existential theory of the reals saying that basically a result of Kani, it says the following. Let's say that we have a formula of the following form. It says, does there exist some solution to what? To some formula, f. What is f? F is a quantifier free. So the only quantifier is those existential quantifiers. In, let's say, and, ors, and nots, I mean, it's not really important, over some atoms. What are the atoms? And the atoms over atoms. What are atoms? Atoms can be either some equation saying that some polynomial is 0, or that some polynomial is at least some epsilon. These are your atoms. Okay, so you have such f. Now, we also need to measure the complexity of the formula, and the size of f is its bit complexity. Complexity, where you think about f as the sum of polynomials, and you take the size of all coefficients, the bit complexity of all coefficients. So you don't think about circuit size. Just think about, you write them down as formal polynomials and sum of polynomials. You look at each coefficient, you compute the bit complexity of it. You take the sum over all coefficients of all polynomials in your thing, plus the size of the formula that you build above them. So it's a bit complexity of.
So this inequality is not scale free. Is that not a problem? Like fx bar is at least epsilon. You haven't normalized the coefficients of f here.
No, I just said this is a theorem. That's, I mean, I'm.
Some numbers are bigger than one, some less than one. You cannot cheat by with this epsilon. It's not all.
Yeah, and epsilon is also part. I mean, it goes into the complexity. The bit complexity of epsilon goes into the thing. It's a part of that thing. So when I say bit complexity, it's a very loose notion, but just understand it. Like if you were to write things explicitly, that would be how much space you'd need. So and Kani says that Kani says that this can be decided in PSPACE. So that's beautiful, right? It's just a beautiful theorem. I give you such an existential formula. You can decide whether this is a true formula or not in PSPACE. So what we'll show is that question 2 of checking whether H is robust or not can be written like this for a formula f of PSPACE of polynomial bit complexity, and that will be it.
I'm not sure. So it's the same x, so there exists an x and therefore.
Yes.
Yeah. So
It's basically, does there exist a solution? I mean, you have a system of polynomials. You want some polynomials to vanish, some polynomial to be at least something, and you want.
So f of x and epsilon, the epsilon depends on x.
But then no, epsilon does not depend on x. Some number. It's epsilon. Epsilon is.
Different epsilons. It's just a constant.
Just a bunch of different polynomials.
Yeah.
This one's 0.
Yeah, that's over atom. Yeah,
You
it's
have
like
one
fi.
in your thing, you have a constant for 1, you can express with 1, you know, you can do 1 over 1 plus 1 plus 1 plus 1 plus 1. And you write it down.
Like in some sense, I don't think.
So what does it mean? I mean,
Epsilon. There's epsilon j you want to write.
it's epsilon. It's part of the epsilon j equation.
In fact, you could have written greater than 0.
Yeah, just let.
Yeah.
Okay. It's the free coefficient of f. That's okay. That's the thing. Okay. And you just want to find whether all those regions either intersect or they satisfy some other thing. That.
Wait, greater than 0 or greater than?
It doesn't matter.
Oh, it's not.
You can. Yeah.
Oh, yeah.
I mean, yeah, because. Yeah.
Yeah.
Okay, so we want to express being, okay, I'll take 2 more minutes or 5 more minutes. We want to express being a robust sitting set in this language. So let's do it. Yeah, so. Sorry?
Would you use or only and?
I mean, I'm using ends, I think. But you have knots as well, right? It doesn't have to be monotone, but.
But it would just be a system polynomial equations or something more complex?
I'm going to use end, only ends. So basically, you want to express. Okay, so as before, we are given age, and we want to ask, does there exist some row such that for every v in our set, this thing is small, so that age is not epsilon robust. But we also want to say that psi is normalized, right? Because it's epsilon robust only for normalized polynomials. So how do you catch that it's normalized? Well, you do something much weaker. You ask, does there exist an alpha such that, yeah, at least something, I don't know. Where alpha is like a small bit complexity in some sense. So basically, that's not, I mean, what we ask is whether, that's another way of thinking about the thing. The psi, I mean, the polynomial psi of x row is normalized, so it has norm 1. It means that it cannot get two small values everywhere. So there should be at least one point where it gets value at least something. And if you restrict the bit complexity of it, then it should get value at least 1. And if you have this property, it implies that the norm is at least something. When you do the epsilon robustness, this will be an even exponentially smaller epsilon than one you started with. But somehow there's something you have to be careful here, but it works. So this is the condition that you want to check, basically. I mean, it's again, it's a much stronger condition, but that's what you want to check. Now you want to express it in this form. But psi is a complex thing. It's a universal circuit, right? It's a circuit. But the point is that you can express psi as a solution to many polynomial equations of degree 2 involving only 2 or 3 variables. And that's very similar to what you do in the Cook-Levin theorem, right? I mean, if you have an arithmetic circuit, you basically you introduce a new variable for every gate. And you just say that if a gate, let's say z, has two sums, z1, z2, and z3, you want z1 minus z2, and then you take the operation between them. You want this to be equal to 0. So it means that z1 computes the right polynomial on those guys. And then you want your output, the output, right, to be at least this. For example, for this equation, you want it to be at least 1. Or you want it to be at most epsilon or something, right, for these kinds of things. So if you take the end of all those equations, it basically tells you that the output computes the polynomial that the universal circuit computes, because that's what those things guarantee. And then you can express the fact that it's larger than smaller than epsilon or larger than 1, etc. This also shows the bound on the degree, for example. But anyways, but that's what you do, basically. Then you take the end of all those, do the end of all those equations, and you feed it, and then you ask, does there exist rho and alpha, etc. And the alpha that you take, you make sure that it has a small bit complexity. Yeah, and then you have to run over these.
Why do you, can't you change with just adding a square to each inequality, another variable, make it equations, use what do you need to do with this tensor theory? You know what the epsilon is known.
How do you do
It's
this?
not bound. It's a bound.
No, but how do you do this?
No, just
Yeah, plus some positive variable.
But it's a different.
Yeah, it's another variable.
But you want to claim that this variable is small.
What?
You want to claim that this variable is small.
This variable is positive. X squared.
But you need at least 0. X squared.
Yeah.
Okay. So you want to say that this with sum t square, tv square equals epsilon.
And
That this is that minus this plus 1 equals some t o square.
Yeah.
And then you ask about the existence of those t's.
These are also valid.
But the number of circuits is, I think to do it for every y, which is too many.
No, this you do for every v.
Polynomials has to do with the
Yes.
size of H.
Yeah, the number of equations has to do with the size of H. So what are the variables? So you ask about,
Rho, alpha, and
yeah, you want to know whether there exists a solution for the rows, for the TVs, TV for V in H, for, I don't know, T of alpha, and you also want to say that alpha is a small bit complex, but that's okay. You just define it. You just define the bits of alpha. Rho, TV, T alpha. And so these are your variables. So yeah, maybe you can put it in P space like this, and then get that it's in PH, assuming Coiron. Nice. No, but see, and this is our epsilon.
that's some fixed number. It's
And in the Nullstellensatz, the complexity is defined as in the bit complexity of the polynomials. In the Nullstellensatz. No, but how do you put it in PH if the bit complexity is polynomial? Ah, that's okay still. It's okay still.
but even before this application.
Yes, you can just do it in yes, actually you can do it like this, I guess, right? You can express your set of, so this shows maybe that Kani also reduces to Nullstellensatz?
Well, I think he needs, in these questions in
No,
robotics, you need the alternations of the quantifiers. You need the ends and alls. It's a real circuit, and I don't know how to do this.
I said just because in our case we have on,
Yeah,
just because we have only the ends.
Of inequalities over the reals, you can translate the system of equations.
Yeah, I think
More variance.
I think that all we take is ends.
Okay, but we can
Right.
debate
But yeah, but anyways, but that's the proof, and there are some obvious questions. Do it better or whatever. Okay.
All right, thanks.